Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video in which we'll graph hyperbolae, which is the plural of hyperbola. So, the simplest hyperbola, y equals 1 over x. So this is new to us. We've seen examples where we're graphing, y equals something times x, or x to the power of something, or even where x is in the power, like 2 to the power of x. But this is new because we're dividing by x. This is y equals 1 divided by x. So let's have a look at what that graph would look like. Let's start by first labeling our axes. So let's just plot a few points. So we can just substitute different x values into this one here. So let's say x equals 1, y is 1 divided by 1, which is 1. So if x equals 2, y is 1 divided by 2, or a half, which would be down there. And then if x equals 3, y is 1/3, which is about here, and then x equals 4, y is 1/4, and so on. But what about when x is less than 1? So we know if x is half, y is 1 divided by a half, which is 2. And if x is a third, y is 1 divided by a third, which is 3. And this sort of makes sense. As x gets larger and larger, y gets smaller. It gets closer to 0. 1 divided by 1,000 is still a positive number, but it's very close to 0. So what's happening is as x is getting larger and larger, as we're going along, y is getting smaller and smaller, or closer and closer to 0. But it will never actually hit 0, because 1 divided by a number can never be 0. On the other hand, when x is getting closer to 0, x is getting smaller and smaller, y is getting larger. If you divide 1 by a really small number, you get a really large number. This gets closer and closer to the y-axis. But once again, x cannot be 0. X can't be 0 because you can't have 1 divided by 0. So we actually call these no-go zones asymptotes. So for our graph of y equals 1 over x, the asymptotes are x equals 0, which is actually the y-axis, and y equals 0, which is the x-axis. The graph can never hit or cross these lines. It can never hit the x or y-axis, so it actually has no intercepts. So we can't have x equals 0, because then we'd have 1 divided by 0. We can't have y equals 0, because you can't divide 1 by any number and get 0. What will happen is, however, that the graph will get closer and closer to x equals 0. Y will get larger and larger. It will go off towards infinity. And as x gets larger and larger, y will get closer and closer to, but never actually hit 0. So they are the two asymptotes. But there's a whole region of the graph we've neglected. We can also substitute negative values into this. So if x is -1, y is 1 divide -1, which is -1. If x was, say, -1/2, which is here, y would be -2. If x is about here, -1/3, y would be -3. On the other hand, if x was -2, y is 1 over -2, or -1/2. If x is -3, y is -1/3. So we've got the same story here. What is happening is x is getting closer and closer from the left-hand side to 0. X is negative and getting slightly larger and larger towards 0. Y is going off towards negative infinity. It's getting really large but negative. And what happens as x gets more and more negative, as x gets smaller, it goes further and further away from the origin, once again the graph approaches 0. Again, the graph can never hit x equals 0 or y equals 0. So this is a very weird graph. It's like in two distinct regions, two pieces, and that's what hyperbola are. So what is in blue is the graph of y equals 1 over x. Yes, this is different because there's sort of a jump between one region of the graph and the other. This is the first function we've looked at that's not continuous. But all the hyperbola we look like will look something like this. So if I say wanted to graph the function y equals -1 over x, that's the same except every time y was positive, we change it to negative. So this point here goes down to this point here, and this point here goes down there, and so on. Similarly, this point here, which was negative, becomes positive by the same amount, and so on and so on. So the graph of y equals -1 over x is actually the same. It's just in different quadrants. It's just a reflection about the x or y axis. It will get closer and closer to 0. Y will get closer and closer to 0 as x gets larger. It's the same sort of thing, and it's going to be in two lots as well. So the red graph is y equals -1 over x, and the blue graph is y equals 1 over x. They are hyperbola in two different parts. So let's look at another example where we're looking at some translations to this hyperbola. Please pause and copy down if you need. So now we're going to look at graphing y equals 1 over x minus 3 plus 2, and it turns out that this is a hyperbola as well. So it looks similar to y equals 1 over x, except we now have this extra -3 and plus 2. So what we do first is we're going to look at the asymptotes, the no-go zones. So what we're looking for here are values that x or y cannot take. So it's easy to figure out the values that x can't take. We can't divide by 0, right? So this thing on the bottom can never equal 0. So we can't substitute into this equation x equals 3. We can't have x equals 3, so x equals 3 is a vertical asymptote. So that's this line here. That means that the hyperbola cannot hit or cross this line. So what about what y values can't take? Well, once again, if you divide 1 by something, no matter how complicated that something is, it can't be 0. What I'm saying is this fraction cannot equal 0. So that means y cannot be 0, that thing in blue, plus 2. Y can't be 2, because if y were 2, then this thing in blue would have to be 0, which I said can't happen. So the other asymptote here is y equals 2. That's the horizontal asymptote. So the graph, we don't know quite what it will look like yet, but it cannot cross this horizontal line either. It cannot hit or cross either of these two lines. So basically, what we've done is we've shifted the graph across 3 to the right and 2 up. Because remember, the asymptotes of y equals 1 over x, they were the y-axis, this line here, and the x-axis, this line here. But we've shifted this vertical asymptote 3 spots to the right. And we've also shifted this horizontal line, this horizontal asymptote, 2 spots up. So other than that, this is exactly the same graph as y equals 1 over x. Now, because we know what y equals 1 over x is, we're going to compare all the hyperbola we graph to that function. So what I've written down the bottom are the transformations you need to know. So y equals 1 over x plus h plus k. It is the same as y equals 1 over x, except it's translated left if h is greater than 0, right if h is less than 0. So the h sort of goes in the opposite direction than you'd expect. It goes left if h is positive. You'd think it would go left if h is negative. But the k works the way you'd expect. It goes up if k is positive and down if k is negative. So how much it goes up or down depends on the value of h or k. So in our example here, we had h is equal to -3, so that's why it goes 3 to the right, because it's right if h is negative, and it goes up to because k is 2. K is greater than 0. So when I say we're shifting the graph, think of it as shifting the asymptotes. The asymptotes are normally x and y are equal to 0, so x equals 0 is this asymptote, y equals 0 is this asymptote. We shift the asymptotes depending on the values of h and k. Otherwise, it's the exact same graph as y equals 1 over x. So what that means is it's almost like this is our new origin, and this is our first quadrant. This is our second quadrant, third quadrant, and fourth quadrant. So we know that the hyperbola went in the first and third quadrant, so it's going to do that again. We might figure out a couple of points just to make sure we know exactly where it is. So if x equals 4, y equals 3, so it's going to go through here. And we know it's going to get closer and closer to the asymptotes. So it's going to go like this. It's never going to actually hit the asymptotes. So if x equals 2, y would be 1 over negative 1 plus 2. It would be 1. It would go through this point here. So other than that, it's the same as y equals 1 over x. So it's going to get closer and closer to the asymptotes. Like so. Okay, now if there are intercepts, we should write what they are. There won't always be intercepts for hyperbola, as we just saw. So let's find the x and y intercept of this equation here. So finding the y-intercept is easy. If x equals 0, y is just 1 over negative 3 plus 2, which is just 1 2/3. 0.6 recurring. So this point here is 0, 1.6 recurring. Okay, and you know from when we did nonlinear relations with parabolas, you know how to find the x-intercept. I just let y equal 0. So I have 0 equals 1 over x minus 3 plus 2. So we can just subtract 2 from both sides. And what we can do is actually flip each fraction. So the reciprocal of minus 2 is minus a half. And then we can add 3 to both sides. So here x will be 2.5. That means that this point here, the x-intercept is 2.50. Okay, so it's just good to mark those. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.